When you have a great idea, like a new ad campaign or chemical formula, your natural instinct is to find data proving it is true. But statistics doesn't work that way. It is mathematically impossible to demonstrate that a statement is definitively true. Instead, statistical logic is designed to do the exact opposite. Statistical logic demands testing the status quo. You don't prove your idea is right. You prove the scenario where your idea has zero effect is unlikely. You cannot test your claim directly. You must formally test the exact opposite. To mathematically support your own theory, you have to surrender direct proof and instead construct an opposing straw man specifically so you can knock it down. In statistics, this paradox is managed through two formal buckets: the alternative hypothesis, or HA, and the null hypothesis, H0. Your actual goal or research claim lives entirely within the alternative hypothesis. But the mathematical formulas require you to test the null hypothesis, the scenario where nothing happened and your idea had no effect. If you set these two up backward, or put the wrong math symbols in the wrong bucket, the entire statistical logic breaks down. The resulting test data will be completely meaningless. The central dilemma of hypothesis testing is that we sacrifice intuitive language in exchange for a rigid scientific rigor that prevents us from falling for false alarms. Let's map out the roles. The alternative hypothesis, HA, is the challenger. It's the claim that there is a real difference, an effect. Because it is the challenger, it only wins if the data definitively defeats the baseline assumption. The null hypothesis, H0, is that baseline. It's the assumption that things are equal to a standard benchmark. This leads to that awkward double negative phrasing. Instead of saying the alternative is false, we say we failed to reject the null. Why the clunky math? Because formulas need a fixed anchor point. Without a specific numerical baseline, like a battery lasting exactly 36 months, probability formulas can't calculate how unlikely your results are. HA is the destination you want to reach, but H0 is the mathematical engine required to get you there. To make this work, you have to translate English claims into math symbols without failing the test. Here is the absolute unbreakable rule of hypothesis formatting. The equal sign belongs to the null hypothesis every single time. H0 must contain the equals condition to create the precise anchor point. This means the alternative hypothesis, HA, can never contain an equal sign. It must always represent an inequality or a directional difference. This is how it looks in a standard textbook. Focus on the center, where the one-tailed null hypothesis is written as H0, mu0 is less than or equal to mu1, while the alternative is HA, mu0 is greater than mu1. If your specific goal is to prove two things are exactly equal, traditional hypothesis testing is the wrong tool. This entire system is built specifically to detect differences. With symbols placed, you must decide how you challenge the null, looking for any change at all or only change in a specific direction. This is a non-directional or two-tailed test. This happens when HA uses the not equal to symbol. It means you're checking if the outcome could be better or worse. A two-tailed test covers all bases, but it splits your significance threshold, the alpha, in half. This makes it mathematically more difficult to prove that a difference exists. A directional or one-tailed test narrows the focus using a greater than or less than symbol. The bell curve shifts, combining those two small zones into one larger rejection region on just one side. The trade-off is the blind spot. A one-tailed test puts all its statistical power into proving an increase. If the outcome is actually much worse, the test will simply ignore it. A directional test gives you a higher chance of proving what you want, but you accept the risk of overlooking unintended negative results. The right setup depends on your real-world stakes. We can map these rules to 3 different profiles. For the exam prep student, focus on the equal sign. Memorize that equal to, greater than or equal to, or less than or equal to never go in the alternative hypothesis. For the business A/B tester, a directional test is often best. If a new website layout isn't strictly better than the old one, you'll stick with the status quo anyway. You don't care if it's identical or worse, only if it's an improvement. For the academic researcher, you generally need a non-directional test. Your job is to report the truth as it is, which requires maintaining scientific integrity regardless of the direction of the change. As shown in this textbook table, researchers use these definitions to distinguish between two-tailed or non-directional and one-tailed or directional tests to manage the risk of false alarms. Ultimately, setting up your hypotheses correctly is all about perfectly aligning your statistical risk with your real-world objectives. The core paradox remains: we support our ideas by systematically disproving their opposites. The alternative hypothesis is your goal, but the null hypothesis is the mathematical strawman that makes the test possible. This framework can feel backward, but it exists specifically to protect us from our own confirmation bias. Hypothesis testing forces us to act as rigorous skeptics of our own ideas. It ensures that when we finally do claim an effect, the evidence has met a high enough bar to make a fluke highly unlikely.